Good afternoon, everybody. I am a bit late because I waited some time to see if some students were joining. Actually, I am aware that today you had other commitments, and so I was not expecting you to join today, actually. In any case, I am delivering the lecture so that you have the video recorded in order to support your preparation for the exam. Okay, so this is our last lecture. Our joint adventure is already going to finish. Of course, we will see each other at the exam. You have the dates, and the first date, as you know, will be late in May. And in any case, if you would like to contact me later on for getting a clarification before the exam or even after the exam, I am, of course, available by email, and you are willing to contact me whenever you want. Okay, so I think at this stage I can share my screen. Just 1 second. I have already my our web page open. Just 1 second. Here we are. Okay, let me share it. Good. You should see my screen now. Okay, so let me go to our web page. Here it is. So we have only 2 links left. I am starting with dredging, and then we will see if we have time. We will move forward by discussing some details related to the design of breakwaters. And but this will be followed. The link will be followed, and the discussion will be started only if we have time. Let's see. Okay, now let me click on dredging in Harbour basins. There is a I have a PowerPoint available for delivering this lecture. Actually, the PowerPoint is not yet available for download on my website. I will make it available soon. And it's also not complete. It covers only the first part of the lecture. But given that the first part is the more technical one, I prefer to use the PowerPoint to deliver in the lecture today. And so here it is, and let me just put it in presentation mode. So we are talking today of dredging. Dredging is an essential maintenance operation that is taken in harbors, in ports, in harbor basins. Dredging is necessary because harbor basins are subjected to siltation. Siltation is a relevant problem because it can cause any impact on the navigation. It can undermine the normal port operations, and therefore periodically port authorities have to undertake dredging operations, which are supported by monitoring and supported by side activities that we will discuss. So why do we have siltation in harbor basins? Harbor basins actually are prone to the deposition of sediments because we have at the entrance of the harbor basin, we have a transition from a high energy environment, which is the open sea, to a low energy environment, the basin itself. And so in all of these situations, you experience siltation because in a high energy environment, sediments are mobilized, and with the reduction of the energy of the flow, they tend to settle down and reach the bottom of the sea. Therefore, you understand the reason why siltation happens, and you also understand that it may be a problem because, as we will see, siltation may be very significant, may reduce significantly the open space that is available to ships for maneuvering for all the harbor operations. Sometimes, indeed, the entrance of harbor basins is protected by groins. Why? Because, as you can see, for instance, in this figure, sometimes the main flux of sediments is directed along the coast. This happens quite frequently. And therefore, in order to reduce the flux of sediments into the harbor basins, very often groins are put in place because they stop the sedimentation and up to their extension into the sea. And of course, you understand that the movement of sediments is very significant close to the coastline. But when you get into the sea, the flux of sediment is reduced. And therefore, if we protect with groins the band close to the coastline where a long shore sediment transport is significant, then we reduce the flux of sediments at the harbor entrance. We know that this type of intervention, this type of protection with groins may originate a perturbation in beach morphodynamics, in coastal morphodynamics. We have seen the video, you may remember, of the case study where the realization of groins has had caused deposition of sediments upstream the flux of sediments and a corresponding erosion downdrift. Like you can see in this picture. In this picture, I highlighted in the left groin the deposition of sediments in red, and I highlighted in correspondence of the right groin the erosion along the coastline. So also the effect of this perturbation is to be considered. But the message that I would like to convey is that we have this problem. The problem may be reduced by placing coastal protections like groins, but overall we need a refined study of the sediment dynamics in proximity of the coastline and within the harbor basin. You understand that in order to plan dredging operations, in order to plan these protections, these interventions, we need to study in detail the dynamics of sediments. Just 1 second, I am checking if somebody of you joined. No, for now, that's fine. Okay, so now, what is influencing the siltation rate? Siltation rates in general depend on the characteristic of the harbor and the marine environment, of course. They depend on the flux of sediments along shore and across shore. They depend on the hydrodynamic behavior of the marine and harbor environment, and also they depend on the climatic condition. Also, climate change may originate sorry, for some reason the presentation disappeared. Also, as I said, the climate change may cause perturbation of sediment transport and siltation. Now, the first important thing to say is that siltation rates may be very important, very significant. And to give you an example, as you see in this slide, in the port of Rotterdam, and precisely in a waterway of the port of Rotterdam, we observed up to 3.5 million of cubic meters of siltation per year, with a thickness of the accumulated sediments up to more than 1 meter per year. So you understand that in some regions, in some particular situation, it may be an important contribution to the reduction of the open space in harbors. So dredging is indeed necessary. Siltation rates depend on several specific features, and in particular, as you can see in the slide, distance from the open sea, area of the harbor basin, area of the entrance in the basin, of course, tidal range and duration, because the dynamics of tides, the evolution of tides and the recession of tides causes fluxes of salt water inside and outside the harbor basin. Also, the peak tidal currents are, of course, relevant. The outside concentration of sediments, of course, and the density difference of sediments inside and outside the basin, because the greater the gradient in concentration and the greater the flux of sediments into the basin. All of these features have to be considered in our modeling, in our assessment of dredging. Just to be clear, assessment of siltation. Just to be clear, assessment of siltation is important because we need to plan dredging operations. So, of course, everything in an efficient management of a port needs to be planned. And in particular, dredging operations need to be planned because they have an impact on the normal exercise of the port operations, of the traffic, and therefore they need to be carefully planned in advance. We have to avoid excessive dredging. On the other hand, we have to avoid excessive siltation. But in order to make this plan, this very detailed plan of dredging operation, we need an estimate of siltation rates. And this is why we are now focusing on the phenomenon of siltation, its causes, and its modeling. Some more details on what is influencing harbor siltation. It's higher, and higher, I mean up to 5 times higher in salt and brackish water conditions than in fresh water conditions, for the higher concentration of sediments and the generation of stratified flow in the presence of salt water. So please be aware of that. In salt and brackish water, siltation may be larger, much larger, up to 5 times than in fresh water. And the reason is not only a higher concentration of sediments. Of course, we expect in brackish waters and salt waters a higher concentration of suspended sediments in the flow. But there is also the effect of the stratification of the flow, which occurs in salt waters and brackish waters. And this stratification is also favoring the settlement of sediments. An issue related to harbor siltation is the degree of contamination. This is a very huge issue, a very important issue. So the sediments that accumulate over the bottom of the harbor basins are usually contaminated. Why contaminated? Of course, because it's water which is subjected to industrial activities. It's water that it's getting in touch with ships, is getting close to industrial operation, including loading and unloading of oil or other substances that may cause contamination. And of course, when we unload, for instance, oil from a ship, we may expect some leakage, the loss of some material which goes into the seawater. And also you understand that the body of ships, it's usually may get contaminated because the ships may go through contaminated environment, so they retain part of the pollution. And also when they load water to get into ballast condition or unload water, they basically may load some polluted water that is then released in other environments. So there are several operations. There are port activities like traffic on the piers, and these activities are causing contamination, and the contaminated surfaces are maybe washed out by extreme waves, washed out by rainfall. And all in all, we know that in the vicinity of ports, it's not a good place where we can have some fun and some relax, some nice bathing, because we know that the water tends to be polluted. Now, the problem with dredging contaminated muds is that we have to displace them, and their displacement is a relevant issue. It's a relevant issue because it's costly, and in some cases it's hardly possible. When there are a lot of muds that are taken by dredging, their displacement could be really an issue. And in fact, even on the Adriatic, on the coast of the Adriatic Sea, there is this relevant issue of displacement of muds. Just 1 second. Once in a while, I check if you are attending. Okay. Very good. So, dredging. Dredging, how can we define it? Dredging is defined as the removal of sediments and mud from the bottom of water bodies. The material resulting from dredging may be used for beach replenishment or other forms of recycling. This is an opportunity for the displacement of the resulting material. Dredging may be carried out with different techniques. We will see, we will discuss them, the main ones, we will discuss them. And these different techniques are characterized by different operational modes and different impacts on the port activity and the environment in general. Planning and managing dredging activities, it's, as I said, essential. It's essential, and there are prescriptions and rules or technical guidelines issued by the port authorities that provide recommendations, provide rules to follow, which in some cases are also imposed by environmental agencies. It's very important if you get involved in the planning of dredging operation that you get the proper information regarding guidelines, laws in force, and rules. And keep in mind that, of course, in different countries, you may have different recommendations. This is an example of a dredger, and it's called a dredge drag, and it's making dredging by suction. So there is aspiration of water which close to the presence of the sediments, and therefore while taking water into this dredge drag, you also bring sediments suspended into the water. And we will see how the technique is performed. And of course, what you get into the boat is a mix of water and sediments, and then the exceeding water, the water that part of the water is released after proper filtration out of the dredge drag back into the sea. So as I said, this is just only one technique that can be applied. We will discuss these techniques later. For now, I just wanted to put a picture so that you can recognize what is the purpose of some strange boats that you may see into the ports, into the canals, because dredging is also operated in fresh water, in canals. And these are indeed strange ships. And then the resulting material, as I said, from the boat is transported over the land where we need to displace it. Now, let me just get into the detail at the stage of sediment modeling. It is a fascinating field. It is a fascinating field because, you know, it's a big task. It's a difficult task to model the dynamics of sediments. Those of you who attended my course on coastal engineering have had some experience in modeling beach hydrodynamics and morphodynamics. And you already know what are the uncertainties, the relevant uncertainties that affect any estimation of sediment transport, any modeling exercise of sediment dynamics. In this specific case, I want to focus on the application of physical models. Also, in the realm of sediment modeling, so we can perform sediment modeling with the usual two categories of models, the numerical model and the physical model, where with physical model, I mean a small scale lab model. We focused in coastal engineering on numerical modeling, and we set up a numerical model for description of beach hydrodynamics and morphodynamics. We also discussed what are pros and cons of numerical and physical models. And we are not repeating this discussion now. You may certainly remember that the physical models have the great advantage that they can handle more easily three-dimensional problems, while numerical models are more convenient because they are much easier to set up with the current availability of computing resources. We also said, and this is the concept that I would like to stress, that ideally we should use both of them. The ideal situation is the situation where a physical model is used to validate a numerical model. In many applications, actually, we may not have enough resources, and the numerical model, in terms of resources, economic resources, is often preferred because it's a bit cheaper with respect to a lab model, which you understand may require important facilities. We already discussed, but just briefly, physical models when we talked about the stability of rock and armor units. And in that case, if you remember, I introduced the discussion of the similarity, the problem of similarity. Similarity between what? Between the so-called prototype and the model. The prototype is the reality, is what we want to reproduce with a small-scale lab model. Now, let me introduce then this expanded discussion, and let's focus on small-scale models, small-scale lab models first. As I said, small-scale lab models are also called physical model. Don't make confusion with the terms, with the terminology. Physical models, the term physical model has a different meaning with respect to physically based model. The physically based model is a model that is based on the laws of physics, and it's a numerical model. We say physical models to mean that they are physically there, and therefore physical models are actually the small scale models which we physically build in the lab. Now, it is extremely important, as we pointed out when we discussed the stability of Harbour units, that we ensure similarity between the prototype and the model. But let's try to better understand what similarity is. Now, let me first say that if we reproduce the reality, the prototype, in a small scale model, then we cause a change in physical quantities, in their numbers. And this change in the amount of physical quantities in their numbers is equivalent to what is obtained if we change the geometric units of the measurement. So, for instance, we know that if we change the geometric units, the value of any relevant physical quantity changes. So, for instance, if we measure the distance not in meters but in kilometers, we know that the velocity, actually the number indicating velocity, changes if we indicate the velocity in meters per second rather than kilometers per hour. And in fact, we have this conversion factor, which is 3.6 to move from kilometers per hour to meters per second. So when we change the units, the numbers of the physical quantities change. So in the same way, the numbers of the physical quantities change when we reproduce the reality in a small scale model, because reproducing the reality with a different scale is precisely equivalent to changing the units. So we need to understand how this physical quantity changes in the model, in the small scale model, because if the velocity of the flow changes, of course, also the effect of any physical quantity that is related to geometry changes as well. Sediment transport is related to the energy of the flow and therefore to its velocity. If we change the velocity of any flow, the sediment transport may change. But there is something that helps us, a consideration that helps us a lot. Dimensionless quantities remains unchanged. They are not affected by a reduction, a change of units, and they are not affected by a reduction of scale. Therefore, this is our guideline. This is our polar star. When we reproduce the reality, a prototype, in a small scale model, we have to make sure that dimensionless quantities are preserved. This is the way we check similarity. And it is very, very smart, I would say. This consideration helps us a lot. It is very smart and provides a firm criteria to assess whether the model is similar to reality. On the other hand, there is to say that we need to identify suitable dimensionless quantities, and these have to be relevant for the processes that we are simulating. So if I am simulating a sediment transport, I need to identify dimensionless quantities that are relevant to sediment transport. I'm not only simulating a sediment transport, I am also simulating a flow of fluid, and therefore I have to identify what are the relevant dimensionless quantities for fluid flow. And this is the exciting part of it. We need to understand the laws driving a process. So we have to understand the laws driving sediment transport, fluid mechanics. We have to understand the physical quantities that are relevant. And finally, we have to identify the dimensionless quantities that are related to the relevant physical quantities. So, as I said, it's quite exciting. And I also would say that it's exciting because you see in the lab an exciting representation of reality, which indeed helps a lot to understand what will happen after the realization of certain structures, what it happens after the implementation of a mitigation policy. It understands, in our specific case, what is the proper planning of dredging operations. Sorry. Okay, so now how to identify this dimensionless quantity? First of all, let's say that experimental evidence has shown, has demonstrated that there are rigorous links between the measurement of quantities of different type, which means in physics, there are rigorous links between the measurements of distance and velocity. And these links are expressed by physical laws. So in the example that I just made, there is the law that we use to estimate velocity, distance divided by time, which dictates the dependence of velocity from distance. And therefore, we can use this law to understand what happens if we change the unit of measurement of, say, length. So how the measure of velocity will change. To understand this, to understand how velocity changes after a change in the unit of distance, we may apply the physical law that allows us to derive velocity. Therefore, we may divide, in general, the physical quantities in two categories. One is the category of the fundamental quantities, for which it is necessary to define the units. The second category is that of derived quantities, whose units can be derived from the units of the fundamental quantities by means of physical laws. So it's clear that once I defined, for the case of velocity, the unit of velocity and the unit of time, so I say I measure the units of distance and the unit of time. So say, if I say I measure the distance in meters and I measure time in seconds, then it's clear that velocity is a derived quantity which is measured in meters per second. So when we basically we deal with a physical problem, we then can identify the fundamental quantities and the derived quantities. Okay, so the number and the nature of the quantities for which we need to define the measurement, and therefore they are the fundamental quantities, is arbitrary. But these quantities must be dimensionally independent. What does it mean, dimensionally independent? It means that their units cannot be derived from the units of the other fundamental quantities. For instance, let me give you an example. Classical mechanics is governed by three fundamental quantities. And three fundamental quantities which conventionally are length, time, and mass. This is classical mechanics. I may identify other fundamental quantities, but their number must remain three, because if I consider classical mechanics, I see that the quantities governing the whole bunch of classical mechanics, the whole domain of classical mechanics, can be described, their units can be derived as a function of the units of length, time, and mass. So there is no other physical quantity in classical mechanics that needs an additional fundamental quantity. Once that I define the unit of length, time, and mass, all the quantities in classical mechanics, all the units of the quantities in classical mechanics can be derived from the units of length, time, and mass. But I said earlier that the number is arbitrary. So there is a contradiction here. Actually not, because I may decide to reduce the number of fundamental quantities. For instance, if I'm not interested in the whole domain of classical mechanics, but I'm only interested in kinematic can be the units of any quantity in kinematics may be derived by the only units of length and time. I don't need mass in kinematics. If I want to extend to dynamics, then I need mass. Therefore, once I have to study a process, I may decide to focus on a limited part of it. And therefore, I may reduce the number of the fundamental quantities. So if I'm not interested in the whole domain of classical mechanics, but I am only interested in kinematics, I can decide to remove mass from the fundamental quantities. I don't need it. So the number is arbitrary in the sense that it can be reduced. On the other hand, once that we defined a process and we defined the quantities that I need to describe, the number of the fundamental units, it's uniquely identified. But I don't want to make an easy story complicated. Let's now to say that in classical mechanics, we need 3 fundamental quantities, and these are usually length, time, and mass. Okay, and the units of these quantities, length, time, and mass, are established by conventions, but we can decide to change the units. So usually in the international system, length is measured in meter, mass is measured in kilograms, and time is measured in seconds. But if I decide that I want to express time in hours and distance in kilometers, this is fine. Of course, you know that it's much better if we refer to the international system for, let's say, for improved communication, but we may change them. And for instance, if we indicate the units of length, time, and mass with the symbol L, T, and M, the new units could be given by the symbol RM, as you see in the bottom of the slide, RL, RT. These are the new units. Now, as a result of the above change, the units of measurement of the derived quantities, as we said, will change. And the U unit for the derived quantity, say A, will have a measure RA, which is changed with respect to the previous unit of A. And this value will depend, you understand that, on the change imposed on the fundamental units. You see the first equation here. RA is a function of RM, RL, and RT. It can be shown that this condition, we don't demonstrate it, it is satisfied only if the function f takes the form of a product of powers, so that the equation becomes, as you can see in the bottom of the slide, RA is equal to RM to the power of alpha A times RL to the power of beta A and RT to the power of gamma A. So you see that the powers are related to the quantity A. Therefore, once I change the units therefore moving to Rm, Rl, Rt, the exponents of the product of powers need to be identified depending on the nature of the quantity A. And this exponent will give to me the means to compute the new unit Ra. So basically, how to determine these exponents? I have to look at the functional relationship that relates A to the fundamental quantities. For instance, if A is velocity V, which is obtained by dividing, as we said, length by time, then we can easily demonstrate that beta A is equal to 1 and gamma A is minus 1. So let me go back to the previous slide. You see here, and beta A is the exponent of length, it's 1, if I want to compute the new unit of velocity. Gamma A is the exponent of time, and it's divided, time, we divide by time when computing the velocity, so gamma A is minus 1, alpha A is 0, because I don't have, the velocity is a kinematic quantity, and therefore I don't have the unit of mass into the unit of velocity, and therefore alpha A is 0. Now, if all the three exponents, alpha A, beta A, and gamma A, are equal to 0, the unit of A does not change, even if the fundamental units are changed. And then we say that A is a dimensionless quantity. It's a pure number. If only alpha A and gamma A are equal to 0, then we say that A is a geometric quantity. If alpha A is equal to 0, only alpha A, like for the case of velocity, we say that the quantity is a kinematic quantity, and dynamical quantities are instead characterized by non-zero values of all the three exponents. I hope it's clear. It is very simple. In practice, it's very simple, and I hope it's clear also in theory, let's say. Okay, now let's move forward. So if we change the units of the fundamental quantities, we can rigorously identify, estimate how the rate of change of the derived quantities, how the derived quantities change. And conversely, the opposite is also true. A new choice for the units of three derived quantities that are dimensionally independent implies a consequential change for the units of the fundamental quantities. Now, what are the fundamental quantities in our case? Our case is, first of all, fluid mechanics, and then there will be also sediment transport. But let's start with, first of all, fluid mechanics. So the fundamental quantities, it can be proved that are the mass density of the fluid ρ, the speed v, and the length L, which are dimensionally independent. And these are often assumed as the fundamental quantity. First of all, how to prove that these three quantities are dimensionally independent? We don't go into the details. We have to study their dependence by putting them into a matrix and making some verifications. We need to put the units into a matrix and make some verification. It is very easy. We don't go into the details because I don't want to bother you with technical details. What is important is the concept. The concept is that if these quantities are dimensionally independent and are in a sufficient number, then we can prove that any other quantity, physical quantity that is relevant in fluid mechanics have units that can be expressed in terms of the units of the fundamental quantities. If you are missing a fundamental quantity, this means that there are some derived quantities whose units you cannot express in terms of the units of the fundamental quantities that you have identified. This means that you need additional fundamental quantities, okay? We can prove that the mass density of the fluid, the speed v, and the length L are dimensional independent, and believe to me, they are enough in fluid mechanics to describe any relevant physical quantity. Now, on the other hand, we can prove that fluid mechanics can be fully described in the absence of thermodynamic, electromagnetic, and chemical effect by 9 quantities, and they are length, time, speed, velocity, acceleration of gravity, pressure, mass density of the fluid, dynamic viscosity of the fluid, compressibility of the fluid, and surface tension. These are 9. But with these 9 quantities, I can describe every process in fluid mechanics, but we also know that 3 of them are fundamental, which means that once I selected the 3 fundamental ones, the units of all the remaining 6 can be expressed as a product of powers of the units of the fundamental quantities. Therefore, what does this mean? If I have 9 quantities and their units can be expressed as functions of the units of 3 fundamental quantities, it means that I can find ratios between the quantities, between any of these properly chosen, any of these 9 quantities, I can find ratios between them that are dimensionless. And the number of these ratios, the number of these dimensionless numbers is 6. It's clear because, I mean, you have 9 quantities. You can express their units in terms of the units of 3 quantities. And then 9 minus 3 is 6. It means that we can identify, we can express 6 of these quantities in terms of dimensionless numbers. What are these numbers in fluid mechanics, or let's say fluid dynamics? Fluid mechanics is more general. What are these numbers? I think you heard of some of them already. They are the Reynolds number, the Froude number, the Weber number, the Mach number, the Euler number, and the Strual number. These numbers are dimensionless, as we said, and therefore their amount, these numbers have to be preserved in the model and the reality to make sure that we have similarity. So this is a driving principle for setting up our small scale model. We have to preserve these 6 numbers. Now, how did we identify these numbers? Just, first of all, we are not providing, not now, the analytical relationship for them. But we identified them by combining the 9 quantities in a way to obtain dimensionless results. There is, on the other hand, the possibility, and I think this is nice and interesting to note, there is the possibility to provide a physical interpretation of these numbers. they can be interpreted, all of them, with the exception of the only exception of the Strual number. These numbers can be interpreted as the ratio between the force of inertia expressed by the term rho L square V square, where L is a characteristic length of the fluid flow, like pipe diameter for pipe flow, the hydraulic radius for the open channel flow, and so forth. So if we put at the numerator the force of inertia, rho L square V square, so mass, fluid mass, characteristic length of the fluid flow, and velocity of the flow. If we put it at the numerator, and we put at the denominator the forces assigned, acting on an assigned volume of fluid, we obtain a dimensionless result, because it is a ratio between forces. So for instance, the Reynolds number can be expressed as the ratio between the force of inertia and the force of viscous friction, expressed by the term μ LV, where μ is dynamic viscosity of the fluid. So the result is, for the Reynolds number, at the numerator you have rho L square V square. At the denominator you have rho LV, and the result is simply rho LV divided by mu, where once again rho is mass density of the fluid, L is a characteristic length of the fluid flow, V is the velocity of the fluid, and μ is the dynamic viscosity. So note that this physical interpretation, force of inertia and the force of viscous friction. So what can you conclude? When the Reynolds number is very large, which means that velocity is large or the characteristic length is large, you have the force of inertia, which is much prevailing over the force of viscous friction. This is physically reasonable. If you think of a fluid with a strong velocity, of course, it has a huge inertia, which means that this force of inertia is much larger than the force of viscous friction, which is something that it's relevant when the fluid moves with a limited velocity. When the fluid moves very slowly, then the viscous friction is relevant. It becomes comparable to the inertia. But when the fluid is very fast, the Reynolds number increases. And the same if the pipe of the diameter of the pipe in case of pipe flow becomes large. If you have a huge pipe, it means that you have a lot of mass of fluid moving. It means that the inertia is huge. So, I mean, the Reynolds number, which may look obscure if you think of it as a dimensionless relationship between physical quantities, it may look like something obscure. You determine it by imposing absence of dimensionality. It's a bit obscure, but if you look at it with the physical interpretation, we have this physical interpretation that is ready, which is very clear. So when I have a large Reynolds number, it means that I have a lot of energy. There is inertia, a lot of inertia. Now, what about the Froude number? I put it in red just to make a difference between the different paragraphs. The Froude number, I'm sorry, sometime once in a while I have the presentation disappearing. The fluid number can instead be obtained by setting the force of gravity at the denominator, which we can express with the term rho L cube G, where G is gravity and rho is still the mass density of the fluid. So the fluid number is given by the forces of inertia, which is rho, again, rho L squared V squared divided by rho L cube G. And then we obtain the very easy expression for the fluid number squared, I forgot to say it before, the very easy expression for the square of the fluid number, which is velocity squared divided by the product GL. Now, what is the physical interpretation? It is the fluid number can be interpreted as the ratio, this is very interesting, the ratio between the velocity of the fluid, because at the numerator you have the velocity of the fluid, and the velocity of propagation of a gravitational wave of small amplitude. Indeed, the square of GL can be proved. It is the velocity of small perturbations in the body of the fluid. So what is then the physical interpretation of the fluid number, which is, as I said, very interesting. Being the fluid number the ratio between the velocity of the fluid and the velocity of the perturbations, if the fluid number is lower than 1, it means that the velocity of the perturbation is higher than the velocity of the fluid. It means that the fluid is very slow. It means that the perturbation can climb up upstream. If the fluid number is larger than 1, it means that the velocity of the fluid is larger than the velocity of the perturbation. So the perturbation cannot go upstream, cannot go along the flow upstream. This is interesting. Just to give you another example, the Mach number is expressed as the ratio between the velocity of the fluid and the velocity of propagation of an elastic perturbation. So you see that for all of these numbers, you may identify a physical interpretation, and this is useful because it allows you to better understand the process. Okay, now, I said before that in classical mechanics, I need 3 fundamental quantities, and I need a lot of derived quantities to describe any process. But in any investigation that I make, and let's continue to refer to fluid mechanics, I can reduce the number of the quantities I am interested in if I am focused on a specific problem that doesn't need some of these quantities to be described. So in fluid mechanics, we said that everything is described by 9 quantities, but if some of them have a negligible or null role in describing the processes I am interested in, and I can drop some of them, okay? On the other hand, if additional processes are to be described, this is another important consideration, such as sediment transport. Sediment transport usually is not considered part of fluid mechanics. So when I said that we need 9 quantities to describe fluid mechanics, I didn't include sediment transport. So if I want to describe sediment transport, and this is indeed our case, one needs to consider additional quantities, like, for instance, the diameter and the mass density of the sediments. It's clear, if I want to describe sediment transport, I need to know the mass density of the sediment. It's very relevant. And also the representative diameter of the sediments is very relevant. And then these additional derived quantities lead to identify two more dimensionless numbers. And these are the particle Reynolds number, which we introduced when we discussed the stability of the Harbour units. You remember that the particle Reynolds number comes into play when defining the pattern of the Shields number. And also another dimensionless quantity is the densimetric Froude number. And these are additional pure numbers. Okay, now, basically, what is the conclusion of the reasoning so far? The conclusion is that if we are interested in describing both sediment dynamics and sediment transport, we need 9 plus 2, 11 physical quantities, and we need 3 fundamental quantities, and we have to make sure to preserve 8 dimensionless numbers, which we elencated, we made a list. Okay, and now, but we also said that if there are some phenomena that are non-relevant, some physical quantities that are not relevant in the study of the processes we are interested in, we may reduce the number of dimensionless numbers to be preserved. This could be, this is sometimes needed because I anticipate the conclusion. It is impossible to preserve all of these dimensionless numbers. Really, you may say, it's really impossible. Okay, let's try to analyze the problem in detail. Let me check if some of you joined. No, okay, good. Now, let's analyze this problem in detail then. So, let's suppose that we modify the units of the fundamental quantities, which let's assume they are L, T, and M. Okay, so let's say that N and M, in this relationship, in the 3 relationship that you see here, the subscripts N and M refer to the measurement taken with the previous and new units respectively. So M is for the new and N is for the previous. Okay, so to get the new unit for length, first equation, I need to multiply the old unit by lambda L. And the same for the new unit for time and the new unit for mass. I have 3 multipliers, lambda L, lambda T, lambda M. For instance, if I want to pass from the unit for length meter to the new unit kilometers, I have to set lambda L equal to 1 over 100 over 1000, sorry, because if I have a measurement in meters, I have to divide it by 1000 in order to get the measurement in kilometers. So you see that the determination of this multiplier is very easy. It's a change of unit. If instead of changing the unit, you pass from the prototype to the modeling to the lab, then the change in units of the length units is given by the change in scale. So if I make a reduction of 10, which means that in the lab I have a model that is geometrically 10 times smaller than the reality, my lambda L will be the scale 1 over 10. So it's very easy to determine these multipliers. Okay, good. Now, basing on the conversion scale of the fundamental units given by the previous equation, one can derive the scale of any derived measure. And you remember that we already said that basing on lambda m, lambda l, and lambda t, if you take a product of powers of these lambdas, you obtain the multiplier lambda a of any quantity a. Now the question, we already discussed also how to identify these exponents. We just have to look at the physical laws. Okay, given that the physical law is the same in the model and the reality, so we can say that, as we already said, going to a small scale model produces the same effect than changing the units of the reality. That's fine. Now, now let's see how we already discussed it, how we define lambda L, lambda M, and lambda T in some specific cases. Okay. Now, so let me just go to this, for instance. Let's refer, I am skipping this slide and I come to it later. Let me refer to the Reynolds number and the Froude number, okay? The Reynolds number and the Froude number are given by these two expressions that you see on the left. And for the Reynolds number, the lambda Reynolds is 1 because it's a pure number. The unit doesn't change, and the same for the Froude number. So let me pass from the two relationships on the left to the system of relationships in the second column. So if lambda Reynolds is equal to 1, right hand side, and the same for lambda Froude is equal to 1, these multipliers can be expressed. Look at the definition of the Reynolds number, can be expressed as the multiplier for velocity times exponent 1, because look at the definition of the Reynolds number, velocity as exponent 1, times multiplier of length, exponent 1, times multiplier of rho, exponent 1, times the multiplier of mu, exponent -1. Froude, again, the multiplier of Froude is 1. So we can write, if we square the expression for the Froude number, that lambda v square times lambda g to the power of -1 times lambda l to the power of -1 is equal to 1. So what I have in the second column is simply the conditions, the two conditions to preserve the Froude number and the Reynolds number. Now, let's compute in the third column lambda v, depending on the two relationships that we see in the second column. From the first one, lambda v is equal to lambda mu divided by lambda L and lambda rho. From the second relationship, Froude number, lambda v squared is equal to lambda g lambda L. Let's then move to the fourth column. Lambda v results from the Reynolds number is equal to 1 over lambda L. Second relationship, lambda v squared is equal to lambda L. You see that they are incompatible. They are incompatible. So what does this mean? If in a fluid mechanics problem, I impose the conservation of the Reynolds number and the Froude number, I get change in unit for velocity that is incompatible. So what is the conclusion? The conclusion is that it is impossible to ensure the conservation of all p-independent pure numbers that characterize the phenomenon unless a unique reduction ratio is used, which is given by the characteristics of the fluid and the acceleration of gravity in the two environments. Since gravity is constant, is almost constant over the Earth, and at least in hydrodynamic models, the same fluid is used, typically water, it is found that the conservation of the pure numbers, which means perfect dynamic similarity, is only reachable if we make a small scale model in the scale 1, 1, which means that we have to make a model that is as large as reality, which is not possible in general. In some cases you can in the lab for small pieces, small machineries, but usually for natural systems we need to reduce the scale of representation. And therefore, if I reduce the scale of representation, let me go again to this figure, you see that it's impossible to preserve the two numbers, Reynolds and fruit. Actually, to be rigorous, I should say that from the third to the fourth column here, I assumed, I didn't say this before, that lambda rho and lambda g are 1. To get the expressions in the fourth column from the expressions in the third column, I assume that lambda rho and lambda g are 1. Which means that I am imposing that the gravity is conserved and the mass density of the fluid is conserved. So again, it is confirmed what is stated, I just stated here. It's confirmed that unless you change the gravity and you change the fluid, if you don't do that, it's impossible to preserve both Reynolds and fruit number. So you may say, what is the point here? And what is the point here? The point is that a small-scale physical model is not reproducing perfectly the reality. On the other hand, there is to say that you may be interested in, you may be not interested in reproducing some quantities, some physical quantities, and therefore some dimensionless numbers. So you may say, you may conclude that in your small scale model, you don't need to reproduce perfectly all the physical quantities, but only those that are relevant to the process that you are investigating. And so in this case, you may decide to drop some of the physical quantities, as I said before, and therefore not to care about the fact that some dimensionless numbers may be not preserved. You decide that you don't care about that. So in this specific case that you see on the slide, do we really need to reproduce both the Reynolds number and the fruit number? Think of their physical interpretation and think at a specific application like pipe flow. I mean, pipe flow, I don't think we really need to reproduce the fruit number. It's not important. What is important is that we reproduce the Reynolds number to make sure that you have full turbulence into the pipe flow. But once that you have reached the full turbulence, so you have reached you have preserved the Reynolds number, it's not a big problem if the fruit number is not preserved, and therefore you may focus only on the Reynolds number. Conversely, in open channel flow and also in marine flow, you know, velocities are very often very low, and therefore it means that also the reproduction of the fruit number may be important, and therefore you may decide to impose conservation of the fruit number and forget about the conservation of the Reynolds number. Of course, any situation has to be studied specifically, and the proper assumptions have to be introduced specifically. Sorry. Now, yeah, I went out of the presentation. Just 1 second. We are here. We have almost finished with similarity, and so this slide is summarizing what I just said. No, sorry, it's not this one. It's this one. This slide is summarizing what I just said, and there is also a link which I am suggesting, which is interesting to explore. And let me now show to you. There is also another link, another link here, and more details on physical models can be found in this web page. It's in Italian, and I derived, you can find here more or less the same relationship as I showed to you in the PowerPoint. I see that there are some formatting problems, and here you can see nice pictures related to some models that were realized in our university a long time ago, actually. This was realized about 50 years ago. It's a hydraulic model of the Arno River in the center of Florence. They used it to estimate the effectiveness of interventions for increasing the river conveyance in Florence in order to get Florence more protected with respect to floods. Now, this is another detail from the same model, and here is the model running under a huge flood. And here again, the huge flood in correspondence of the old bridge. This is the old bridge in Florence, you may recognize it. And this is another model which reproduced the effect on the hydrodynamics of and sediment transport of the Reno River close to Bologna, after the construction of the new highway connecting Bologna to Florence. And here you don't see the bridges there. I don't think I have, but you see the piers. This is the old bridge of the old highway, and this is the new bridge. And before constructing the new bridge, they wanted to see if the bridge had any effect on the river flow. Actually, the new bridge doesn't have any pier into the flow, so it was not expected a huge impact of it, but we wanted also to check if the protections, you see here there are boulders to protect the foundations of the new piers. We wanted to see if these protections were effective in actually protecting the foundations of the new piers. Okay, good. I think there is also a video here. Just 1 second. I'm not really sure if I put a video. No, I would say no. You can find many video of hydraulic models on the web. If you look on YouTube, hydraulic small scale model. Let's see. it's not immediately, because here we have a video, but I don't think it is immediately. Now we have the usual, let me see. Yeah, let's see, skip ads. And here maybe, let's see if there are some interesting. No, this is a lecture. Here there is a nice video of a flume, an hydraulic flume, and just 1 second. I think this is much more significant. Wave tank demonstration is more significant for our specific case. Just one second. We wait for. Okay. And let me just move forward. You see, this is an example of an hydraulic model. Okay. I think we can go back here and just 1 second. And now let me make a quick conclusion. So what did we learn today? We learned that in order to describe siltation in harbor basins, we often refer to small-scale lab models. Small-scale lab models are smaller representation of reality. Once we reduce scales, we have to make sure that the physical quantities, the relevant physical quantities affecting the process are properly reproduced. How to make this verification? To make this verification, we have to identify the relevant physical quantities. We have to identify the relevant dimensionless numbers, which are as many as the number of relevant physical quantities minus the number of the fundamental quantities. And then we have to check if these dimensionless numbers are preserved after we make a change in the scale of the units of the fundamental quantities. I anticipate that it happens frequently that the dimensionless numbers are not preserved, but are almost preserved for the purpose of our application. And this is the principle that we need to pursue, the condition that we need to ensure to make sure that the results that we obtain in our small-scale physical model are reliable. Once that we made sure that the results are reliable, once that we made sure that the dimensionless quantities, relevant ones, are preserved or almost preserved, then we can use the model to study what happens in terms of siltation and what happens after dredging. And this allows us to make plans for scheduling the dredging operations. And it also allows to better understand how to make the dredging operations, because once that the model is in place, we can make as many experiments as we want. There is a limitation given by the available resources, but still we can make several experiments. And at this stage, we can easily get support for planning our contributions. Okay, I think it's time to make our break. So let me share the screen and let me stop the webcam and the micro. See you in 15 minutes. I leave the video running. Bye. Okay, here we are. Give me only 1 second. I wanted to check if I can find a video on hydraulic models. Okay, I think this is a relevant example. Just 1 second. I want to start with this video, and let's. Okay, that's perfect. And let me. Okay. Okay. Nisba, I cannot do that because I tell you, I wanted to show you a video on YouTube on an hydraulic model of a port, a facility, but it's on YouTube, and I cannot include a YouTube video into my lecture video because when I put it online, then there might be some copyright problems. So I apologize. Maybe that at the end of the lecture, if we have some time, we can show it without recording. But now I would need to stop the recording to show it. Okay, perfect. But in any case, if you see on Google, if you search in Google for hydraulic models, you find a lot of videos that are interesting. Okay, perfect. Just 1 second. I can close the PowerPoint now because I think we got to numerical models, and then that's it. I will make this PowerPoint available on my website later on. Just keep in mind that for the numerical models which I am treating now, there is no PowerPoint. So the numerical modeling, and here I show you an example where there is a visualization of a numerical model of sediment dynamics around sorry, not sediment dynamics, it's hydrodynamics around a coast. Numerical modeling, we discussed it already, presents the advantage of allowing more efficient and economic development of meaningful models, with the downside that there might be problem in interpreting and reproducing highly complex environments. Because you know, in numerical modeling, the definition of the geometry, the definition of the boundary conditions, everything is potentially affected by uncertainty, which means that the results may, more or less in the same way as small-scale modeling, may neglect some boundary effects or side effects, which is part of the game. We are making an approximation, and therefore we know that these approximations may leave some room to subjectivity and to potential imprecision in the representation. However, they are today largely used because the increasing availability of computing power and the increasing availability of Earth observations and therefore the increasing opportunity of representing with fidelity numerical models the Earth system provide interesting perspectives with also the within a time frame that looks very convenient with respect to laboratory experiments. You may have heard of digital twins. Digital twins are numerical attempts to reproduce digitally a perfect replicate of the Earth system. And these digital twins are increasingly used also in coastal engineering. We are now in a situation where I think for technical reasons, still the best solution is for technical purposes. The best solution is the integration of the two approaches, because this allows to profit from all the available information, thus minimizing the uncertainty. It is anyway a difficult task, because putting together a numerical model plus a small scale model requires a lot of resources, requires the coordination of different groups, usually, or different research groups. But still, for very important interventions, for very important assessments, this is what it's usually recommended, to use the small scale physical model to validate the numerical model and then put together the results. Also, the numerical model has the advantage of being more flexible. Modifying a small scale lab model may be difficult, while modifying a numerical model only requires to modify a numerical setting, so it's not a big issue. So once that the numerical model is validated, it may give the opportunity to more extensively evaluate the results. Okay, so now I said that we may integrate the two solutions, and we may integrate the two solutions also by using mixed models. And another interesting opportunity is given by simplified models. In fact, it is very frequent that we evaluate sediment hydrodynamics and morphodynamics with empirical and heuristic approaches, which are useful for obtaining a first approximated solution, which may be useful for preliminary design. Also, these empirical models, which are based on interpreting observed data, so usually they interpolate the outcomes from field experiments, they are frequently more robust with respect to more complicated approaches. So for getting a first estimate, for getting a first assessment of what happens, they may be indeed an interesting opportunity. A first example of a very simple numerical model, which is basically an empirical model, is the one line model, which is described, which we considered when in coastal engineering we studied sediment dynamics and morphodynamics. Let me see if this link is no, this link is still not correct. I will correct it. Now I want to show you an example of an even simpler model, which is called the zero-dimensional model, which treats a given harbor as a tank. This one that I am presenting here is an approach that was proposed recently, about 30 years ago. And here I am presenting a modified version of this model. And basically, you see here, just one second, you see here that the Harbour Basin is treated like a tank, which is characterized by concentration of sediments, CE, and is characterized by a surface S. It's characterized by the depth H and the volume of the Harbour basin V. And then we have the ocean outside with a concentration of sediments CH. And then we have fluxes Q in and Q out, which are the water flows entering into the basin and outflowing from the basin. Now, under this very simplified representation, it is very easy to impose the mass balance of the sediment. And if you see the first handwritten equation, we have on the left-hand side the change over time of volume of the basin, which depends on time, multiplied by the concentration of sediments into the basin, which also depends on time. So volume times concentration, you have the mass of the sediment. So the volume times concentration gives the mass of the sediments. So the left-hand side of this equation describes the change in sediment mass over time, and which is given by the inflow times the inflow times the concentration of outside sediments minus the outflow times concentration of the inside sediments. And then there is a term Fs, which is the time varying siltation rate. So it is expressing the mass of sediments that settle down per unit time. Okay, and therefore the siltation rate Fst can be written in the form of the product of the siltation velocity Ws times the surface of the basin times the concentration, the inside concentration of sediments. And so by putting together these two equations, what we obtain is that we have the third handwritten equation after the hypothesis of volume of constant volume, which is written in red here. We get that the change in inside concentration is given by second-hand side, right-hand side, is given by the inflow divided by volume, which multiplies the outside concentration, minus the outflow divided by volume times the inside concentration, minus the time varying siltation rate divided by the volume. So finally, we get that the change over time of the inside concentration is given again by the inflow divided by volume times the outside concentration minus the inside concentration, which multiplies the outflow divided by volume plus the siltation velocity divided by the depth. And here we can integrate this equation to describe the change over time of the inside concentration. Of course, we need an initial condition here, an initial condition for inside concentration. We may assume that the outside concentration CH is constant, and then we can integrate numerically this equation provided that we know Q in, Q out, outside concentration, and we also need to fix the siltation velocity, which may be constant if you wish. And we need to define the volume, which we, as I said, we can assume constant. We need also to know the depth H of the basin. So this is a very simple model, which is anyway providing very useful indication. It is indeed a model that is indeed frequently used. In steady state, which means at the equilibrium, such model tends to a configuration that depends on WS and gives assigned siltation rates. In a steady condition, the model lends itself to a numerical solution. There are other examples of empirical and semi-empirical models. We don't move forward. We don't go forward from here because I think what we discussed, what I presented is just fine for our purposes. The important thing is that at the end of the story, we need to come out with a plan, and the plan must be based on monitoring. Monitoring allows us to define all the features that we discussed so far, like the depth of the basin, the evolution of the siltation, and the progress of siltation, and allows also to define the changes in the depth of the basin, etc. So monitoring, it's indeed an important piece of the story, should include an assessment of the bathymetry of the dredged area during interdredging periods. Also, you have to realize that siltation is more significant, it's higher after dredging. So dredging operation, on the one hand, they clean the bay. On the other hand, they cause an increase of siltation, a new increase of siltation. We need to measure the contaminant concentration. So contaminant concentration, I mean the quality of the sediments, so the concentration of contaminants into the sediment. And this is important because it is important for planning the displacement of the muds and the sediments that we dredge. We need to measure the total suspended solids or turbidity in the dredge area, and also if we are dealing with the channel, also downstream, to monitor to monitor the resuspension of the sediment, how it goes, because when we dredge, indeed, there is this side effect that the sediments are resuspended, reallocated in suspension, and this is a problem for the environmental quality of the bay, and it's also a problem for the environmental quality of the ocean outside the bay, because dredging actually increases the concentration of sediments during dredging operations in the bay, inside the basin, and therefore you have also an increase of concentration of sediments outside the basin. And this is something that may cause indeed problems. Let me check. Yeah, if it's still shared the screen. We also need to, in terms of monitoring, just 1 second, because for some reason, okay, I see why. For some reason, it didn't scroll down. We need also to measure air and water quality, and also it's important to make a prediction, to elaborate a prediction of flow conditions during dredging operation, for the same reason that I mentioned before, that we have to control in some way the displacement of contaminants into the basin. Monitor is also useful to assess whether the targets of the design dredging have been met and to provide technical and administrative reports to the relevant authorities. So usually they require careful monitoring before and after any dredging operation, in particular for bathymetry, and also in particular for quality indicators of environmental quality. Now, in terms of planning, dredging is a potentially risky operation that must be supported by adequate planning. As I said, it's risky and also impacting on the port operations. So administrative and regulatory requirements are an essential constraint that one should take into account during the planning process. And for instance, and to provide an example, in Italy, dredging is not allowed in the marine archaeological sites, in the areas with relevant biological and ecological value, in the zones of repopulation in terms of fishery, in the proximity of coastal areas with relevant environmental value, in the presence of underwater cables and pipes and other areas that are specified by local and national regulations. Furthermore, it is prescribed to minimize the environmental impact of dredging through a series of cares, which include minimizing the water content of the removed material. Of course, as I said, there are several reasons for that, but it's also a requirement to make sure that the environmental impact of dredging is minimized. We need to minimize the dispersed material, and we have to limit water turbidity and the mobilization of pollutants, based on detailed information on preliminary classification of the material to be dredged. We also need to carefully assess the economic effort that is needed for dredging. This is strictly related to the management, the actual management of the port. Of course, a port activity needs to be sustainable. Sustainability is also ensuring that all the essential cares are taken for port management. It's clear that if the port management is barely sustainable, then we may undergo a more significant risk of environmental impact. And therefore, we have to make sure that everything is planned in the proper way. And then let me discuss about mud characterization and disposal. So, as I said, this is a relevant issue. It's a relevant issue because muds are invariably contaminated, and it is so an emerging problem, the disposal, for several harbors. And first, we need to make sure that the quality of the mud is characterized. And if the sediments are clean, or let's say they are never clean, but if they are close to clean or can be cleaned after treatment, then they can be used for land filling, for instance, to support land reclamation or beach replenishment. Maybe a good opportunity. Beach replenishment is an important intervention in terms of recovery of the beach value, and therefore, if the two operations can be combined, this is an excellent opportunity. However, I must say that this is very rarely the case because of the contamination of muds, because of the different nature of different characteristics of muds with respect to the original sand of a beach. Now, there are several case studies of reuse of dredged material in the website that I am linking here. Let me open it in a new a website that is the website of the Central Edging Association. And here there are a lot of case studies. So look here, for instance, reuse of dredged sediment on the Caledonian Canal at Lagan, coastal defense and habitat restoration at Horsey Island, land-based confined disposal facility turned into a nesting area. So there are several case studies of phytostabilization, technosol and brownfield biofuel. So several case studies feeding the natural system where they are trying through this association to make systematic the reuse of dredged material. There are also, you see here, using dike construction reinforcement. There are also examples of use of the dredged material to make bricks. I'm not sure whether there is a description of this case here. In this case, there is use of sealing material, use in dike construction reinforcement, and here use in expansion of port terminal. This is a nice case study which I looked at last year. So you see here there is a port terminal that is realized through land filling. You see, this is the picture during the construction works. Land filling, and the land filling is made with dredged material. So indeed, there is a lot of research on the best opportunities for the use of contaminated muds. And let's now open this also this one more link. This again, it's the link of expansion of port terminal. Yeah, the same link that I just explored. Now, here you can see a schematic representation of the workflow for mud treatment and disposal. And in this case, we talk about mechanical dredging. What is mechanical dredging? Is the mechanical removal of sediments through, for instance, a boat that is scrapping the dredged material and bringing the dredged material to the land. So what they do here, look at this figure because I think it is interesting. What they do, first of all, they use a screen in order to avoid that the suspended material goes into the sea. So they use a screen behind the boat, and then they have the dredger, which is it's a mechanical dredger that is scraping the sea bottom and getting a flux of water into the boat, flux of water that transports the sediments. And then through a pipe, the water plus sediment is brought in a sludge basin. This is a typical configuration. And from the sludge basin, there is the subsequent extraction of sediments after the partial settlement. So there is in the sludge basin a first separation of sediments from water, and then they collect, they bring the sediment over the land. Some water is still there, and therefore they mechanically separate the sediments from the water, send the water to a treatment plant from which it can go back to the ocean. And then the removed sediments, which may be salted, by the way, the removed sediments are used for the purposes that have been pre-identified. So from the dredge, you see the workflow from the dredge to the sediment and water barge. We may have also a debris barge if there is a combination of sediments with debris. And then there is decantation, water treatment, discharge, or sediment and debris separation, production of debris, etc. And this is an interesting example of mechanical dredging. And so let's go back here. Now, to give you an example of what parameters may be monitored about to perform the characterization of the mud, we usually monitor the in situ wet bulk density over the depth of the deposits, the sediment composition in terms of fraction of clay, lutum, and the settling velocity, the consolidation parameters, the critical shear stress for erosion, and the yield stress and flow point stress. You don't need to go into the details for these parameters. I'm just providing them for your information, but they are not the subject of questions for the exam. Give me 1 second, because before we talk about wet bulk density, which is an important parameter, now let's go down again. Okay, so now wet bulk density is an important parameter for dredging operations, which may condition the treatment of the mud, and the dry density of sediments can be expressed as a function of porosity, defined as the volume of voids per unit volume of the mixture, and namely what we may define the porosity according to this relationship. I'm sorry, when I teach alone, it's hard for me to keep the concentration. This is the porosity, which is defined as the volume of voids divided by the total volume of the mud, which is given by the sum at the denominator of the volume of voids plus the volume of solid. Okay, and therefore the dry density of sediments, it's expressed as a function of porosity. And in particular, if we indicate the dry density with this symbol here, ρdm, this is equal to ρs times 1 minus porosity, where ρs is sediment density. Okay, so the dry density is given by the sediment density, which multiplies 1 minus n, and ρs is the bulk sediment density. Porosity is related to the amount of water contained into the mud, which one generally needs to extract. We need to extract water before disposing the mud itself. In fact, you know, the problem is that it is salt water, and therefore there is also the problem that water, if we displace sediments with water, we displace an increased volume. And therefore, given that landfill sites are today becoming scarcer and scarcer, it is important that we try to use the landfill volume in the cheapest possible way. Just 1 second, I log out here just to get some more space. Okay, good. Let me just, okay, now let's discuss the different dredging techniques. Okay, sorry, I forgot to say, in terms of the watering, there are two main dewatering methods, the passive and the mechanical. And basically, passive means that we leave the mud there, and we leave there enough time to allow water to flow out from the bulk sediments. Mechanical is done through the help of mechanical forcing in order to make the removal of water faster. Solidification is also commonly used as a sediment dewatering method. Now, dredging techniques. The three main ones, the three main techniques that are used are included in the following three categories: suction dredging, mechanical dredging, and water injection dredging. I already discussed a little bit the suction dredging. Is operated by using a simple suction at the open end of a suction pipe that is covered by a grid to avoid the entrance of large objects. It is a technique that is recommended for sand extraction rather than the removal of consolidated layers. The soil may be loosed by the eddies of water flow only, with no other mechanical action, or the suction head can be equipped with a cutting mechanism at the inlet. In this case, some textbooks classify this technique as mechanical dredging, but it is not important, the classification. The important thing is to understand how it works so that we know what are the means that we may use for dredging our harbor basin. By moving the suction tube at a proper speed, a continuous removal of sediments can be obtained. See the figure here, where we have indeed a cutter head here. And here again, there is the figure of the suction dredge barge. And very often we need some spuds in order to hold the barge in place. And very often, instead of accumulating the sediments over the boat, we have a discharge line which brings the flow that was taken of water plus sediments through a pipe to the land. Mechanical dredging makes use, as you can understand, of mechanical tools to loosen the soil and lift the sediments at the land level. It typically involves the use of an excavator or another type of heavy equipment that is usually placed over a barge or over the land with a long arm. For instance, it's used for dredging the canals. Usually we use an excavator that is placed over the levee with a long arm in order to move the sediments. This is a typical example of a mechanical dredge which is using a clamshell. Let's read here from the site of the Federal Remediation Technology Roundtable. Let's just see if the link is still working. I think so. Let's see. It looks like it's not yet not working anymore. Let me see. This is strange. Maybe it's a temporary problem. Just 1 second. I want to search it on Google. Yeah, I think this is temporary. Please try again. Anyway, this quote from the website says that mechanical dredges are used digging buckets, such as a clamshell, suspended by a cable from a crane, an excavator, or a fixed arm, or dragline buckets suspended by a cable from a crane. Mechanical dredges remove sediment with a similar density and water content as the in-place material. Some water is added to the sediment because the clamshell and bucket are not always completely full of sediment, and therefore the void is occupied by water. Mechanical dredges typically add a water volume that is 0.2 to 0.5 times the in-place sediment volume. Some sediment also is released into the water column as the bucket is raised. Environmental dredging buckets, having specially designed seals, often are employed to minimize release of sediment during dredging. This is a schematic of a bucket dredging, and Here you see again bucket dredging, and this is instead a picture of a clam shell that is working in order to dredge from the bottom of the sea. You see that it's operating from a barge and putting the muds on board. It is interesting to look at this figure. This is a very famous cutter suction dredger called Majur, and it is operated by the Suez Canal Authority in Egypt. When it was first launched in 1996, it was said to be the largest and most powerful cutter suction dredger of its kind at the global level, and was designed to dredge abrasive sand with gravel, compacted sand, sticky clay and rocks in the widening and deepening of the Suez Canal to allow even the larger ships to pass. Its numbers are impressive, just to give you an idea. The total installed power is more than 22,000 kilowatts. The length of the hull and length overall are more than 110 meters. And the width is 22 meters. The maximum draught is 7 meters. The maximal dredging depth is 35 meters. The cutter power is 3,000 kilowatts. The diameter of suction pipe and discharge pipe are 1 meter and 85 centimeters respectively. And the Majur was used to clear the Suez Canal after the blockage that occurred at the end of 2021. If you search in Google for Majur and images, you see here, this is the boat. You see, it's a big stuff. Good. Water injection. Water injection dredging is a relatively new dredging technique, and water injection dredger uses a small jet to inject water under low pressure to prevent turbidity increase in the surrounding waters. So water is injected into the soil layer to fluidize it and originate a turbidity current. The jet nozzles are mounted on a horizontal tube that has a length between 4 and 15 meters. And so the mobilized sediments then flow away downslope along the sea bottom for the effect of gravity. Gravity, and also there is the effect of naturally or artificially induced currents and sediment concentration gradient. The dredge has to keep moving to avoid low density of the water-soil mixture, which may result in the dispersion of the mixture along the whole water column. Here there is a description of some parameters that we need to ensure reach target values. First, it is necessary to mobilize and maintain a high velocity and high concentration flow of mud. This implies that the densimetric fruit number of the mud flow should be larger than 1. So we have to get to supercritical mud flow. The fruit number of the mud flow is given by the relationship that you see here, with V being the mud flow velocity, H the thickness of the mud flow, ρ the mud density, and delta ρ is given by PS minus PW times C, where PS is mass density of sediments, PW is mass density of seawater, and C is the concentration of sediments. Okay, second, the high concentration mud layer should be stable and its stability depends on the local Richardson number. We don't go into details. I just wanted to emphasize that we have guidelines in some places suggesting conditions to be met to make sure that the dredging activities are fully sustainable. Now, here we have a video, but it's on Vimeo again. But there is a video which I suggest you to look at. It illustrates how water injection dredging works. Good. So, conclusions. It has been a long lecture. I'm not sure I succeeded in making it not boring. Dredging is an important operation for port management and maintenance. As we said, it should be based on the understanding of the local marine condition and sediment dynamics, and therefore we need a monitoring plan, and we need a dredging plan. And mud disposal is today probably one of the most critical issues. There are several experiences. You may find a lot of information over the web. Several experiences on the use of mud material after dredging, on the reuse. On the other hand, it still remains something that is relevant. I just want to mention that in Ravenna, the Port Authority has also to manage a lot of dredging, and how to efficiently plan the dredging operations, how to reuse the dredged material is one of their main concerns. Okay, I would say that we are done for dredging, and keep in mind that questions at the exam may be asked regarding similarity. And in particular, what I discussed in detail today, please make sure that you have a good confidence with it. Also, questions may arise about the zero-dimensional model, this one, because this is a quite simple relationship that I suggest that you learn by memory, because it may be a question at the exam. And also, I think the model is very significant for both gaining a better understanding of how the process works. It's a simple process, but I think a conceptual model helps to better understand how it evolves. And also, the empirical model is also relevant because it is actually used in practice. And then please be prepared to discuss about small-scale physical models, why they are an interesting opportunity, why also numerical models are an interesting opportunities, what are the pros and cons of these two different approaches. Okay, now I think I have prepared a last lecture, but on the design of breakwaters. I know that Professor Archetti also focuses on this problem. In the past, I managed to agree with her some details that would be explained by me. On the other hand, I think that, this year I added material like Harbour oscillations to my study plan, to my list of topics, and therefore we don't have the time to look at these additional details of breakwater design. Actually, I don't think they give to you, they tell you much more with respect to what Professor Archetti has already discussed with you. So I think it is, we can stop here. And I will remove the link to the design of breakwaters so that you don't get confused on what you have to study. Let me now make a final recap of our experience together. First of all, today I'm finishing a bit earlier, and because you know, when I teach alone, it's it requires more concentration. On the other hand, given that we avoid any interactions take time, and therefore I actually today I was able to save some time. Overall, I think the subject evolved as I predicted. We had limited interaction between us, but I fully understand why. And I hope that we get an opportunity to meet in person at the exam. Of course, the exam has to be taken in physical presence, and I'll make an effort to, me and Professor Archetti will make an effort to make the exams together so we can meet. I just wanted to make a brief recap of what we did together in order to clarify what could be the questions at the exam. So first of all, the first link, this is not relevant for preparing your exam. I think it is a relevant information. The first link is titled Harbour and Coastal Engineering, the learning process adopted in the course, as you may remember. I think it's relevant, but not for the exam. And in general, not for your specific background in harbour engineering. Now, there is a premise, as you may remember, on coast management and beach design. Here, there is some information that you may find you may find in some of the questions which I will ask at the exam. What is a coastline? Classification of coastlines, and so different types of coastline, and then the social function and value of seaports, the social function and value of beaches. You know that the first question of the exam is a descriptive one. It's a question that allows you to speak. So I may also ask some questions which you need to reply to with a narrative, like the social function of beaches. Okay, port planning and environmental impact is a more technical lecture. Load estimation, this is something that it's important. And design life, it's important. Just try to remember some of these design lives here. Berth structure, what type of berth structure we have. This is another possible topic for the exam. Suggested dimension and loads. So the rules of thumb, when there are rules of thumb given in my web pages, please make an effort to have them in your memory and clear, because as you know, I think the rules of thumb are extremely important. And environmental impact, I wouldn't say that there is much that you have to study. Now, forcing estimation, this is probably one of the most asked lectures at the exam. So first of all, definitions for these typical dimensions of typical size, or these are definitions of dimensions that are used to define the ship size. Mooring loads, and a typical question is wind forces. Also the wind rows may be asked. What is the wind rows? Another question may be, how would you define probability? And you have to say with the axiom of Kolmogorov. Frequency and Bayesian definition is also important. What is a probability distribution? This is also important. And then I would say that that's it. Wind classification and wind forces against ships, very classical question. What is ballast? And wind forcing means that you have to learn this equation, as I already told you, how to write it down, and also what follows this equation. So here there is really little material that you can skip. Also, the terminology and function of each mooring line are maybe the subject of a question. And vessel rotation as well, wave forces, not the formula. So a question may be how would you compute wave forces, but you don't need to know the formula. Definition of return period, yes, and also the definition of these terms, nautical terms, the most important one, like the ones in this figure, may be asked. Keep in mind that there are not many of these definition terms that you will need to learn. I would say load by currents, it's just important that you know what is and you can say something on the estimation methods. Okay, and then we have Harbour oscillations. Yes, almost everything here is relevant for the exam. You have to explain why it is concerning. You have to explain how it originates. And you may also want to explain this mathematical formulation for Harbour oscillations. And also pay attention to the terminology. Okay, good. Climate change, nothing to study for the exam. I think it's a very interesting lecture, but don't be concerned by the need to study it for the exam. Beach protection strategies and structures. Yes, a typical question may be precisely what kind of beach protection structures you know. It is a narrative, but on the other hand, it's something that it's important, and I would also say extremely relevant for sustainability. Design of groins, the lambda rule, yes, this is something that is frequently asked, and also typical sizes for groins. This is something that can be asked. How to displace groins, displace the spacing between them, and typical dimensions, as I said, and that's it. Stability of rock and armor units, yes, the sheets criteria. You have to know everything of it. And for these equations on the effect of slope, I don't think it's really needed that you learn them in your memory. The Hudson formula, don't learn it by memory. Okay, dredging in Harbour basins, there is not much that can be asked, but some questions on similarity and the zero-dimensional model, this one, as I just said. Okay. Now, if you need any clarification, if you need any appointment with me for getting clarification on what I taught, you're welcome to contact me by email. Most likely, I will fix an appointment on Teams. I think it's the easier way of giving further explanation to students. And for any question you may have, you know that I am at your disposal. So I think that's it. And as I said, I am a bit early. It has been a pleasure, even if we didn't meet so much. And I hope you appreciated my way of teaching. And one last thing, I am opening the questionnaire for getting your opinion on my teaching. Even if you are a few students only, I will send you through the chat in Teams and through Virtuale the codes for giving your opinion to me. It is extremely important, this survey, even if you are a few students only, because for me, it's extremely important to get your feedback, and also keep into account that also the university uses it for distributing the resources to the department. So it is a case where your opinion indeed matters, and therefore please take this opportunity. By email and chat, I will give you all the details for the compilation of the questionnaire. So again, thank you very much, and see you at the exam dates. And most probably you will find both Professor Archetti and me. I'm looking forward to see you in person. Great. Let me close everything here. They share the screen, and now I can leave you. Thanks. Bye.